Hello, here we will use some facts from linear algebra and orthogonal geometry to interpret volumes as determinants. Volumes of special geometric shapes. So let's imagine we have a collection of vectors and can assume that this collection is linearly independent, and then we could use this collection to create a parallelepiped generated by them. It will be all points in the vector space which are linear combinations of those vectors with coefficients squeezed in between 0 and 1. To illustrate, let's look at a two-dimensional shape of that sort. So we have two vectors, v1 and then v2. And then what we have to do is to continue summing up these vectors sort of, and then the parallelogram, which is a special name of two-dimensional parallelepiped, is this area. And how do we compute the area shaded? Well, the standard method is cut and paste. So if we just drop the perpendicular and then say drop it here, cut this triangle, put it on this side, we will have a rectangle and its area is easy to compute. So we'll be calling area two-dimensional volume, because in general we will be dealing with volumes of m-dimensional shapes. So volume of the parallelogram spanned by these two vectors, generated by these two vectors, is the same, just making this argument algebraic, is the same as the volume of the rectangle. So what are the vectors generating this rectangle? This is v1, and then the vector which is the orthogonal component when we project e2 down to e1. So that is v2 rather. That is what we can call e2 if we are doing Gram-Schmidt process. And if we're doing Gram-Schmidt process, the v1 is also called e1. So that is the Gram-Schmidt orthogonalization of the original two vectors. And then the volume doesn't change through this Gram-Schmidt process. That is this geometric argument of cutting and pasting, and then the volume of this rectangle is just the product of length of the sides, so the length of these two vectors. When we proceed to the next dimension, I will draw the picture, but again we'll have a base and we'll have some height, and this height again, or rather some vector sticking out of the plane of the base, and then the volume is the same as if we just compute the height of that vector over this plane and then multiply the area of the base by the height. Again, the argument is geometric, cutting all the protruding parts and sticking them back to make a rectangular prism, and then the base can be again adjusted by this argument. So that is in effect inductive, and writing it in terms of these volumes, what we start with are arbitrary three vectors. This is v still, and then changing the third into its height, which is sort of this orthogonal thing, which we also call E3 if we do Gram-Schmidt process. So E3 will be the vector which is orthogonal to these two, and its sum with the projection of E3 to these two will be V3 itself. And then we could continue doing this argument and write the volume as really the volume of the parallelogram, or rectangle in high dimension, three-dimensional rectangle spanned by these three vectors. And that is, of course, the product of psi, of lengths of the sides, and in the terms of orthogonal algebra, it is the product of norms of these three vectors. So that illustrates the general principle. If we start with m vectors, starting from the last and going one by one, we can turn them into their Gram-Schmidt orthogonal versions, and the volume will not change in the process. So this is again Gram-Schmidt process results. And then this volume, since they are perpendicular now, this volume is just the product of dimensions of the sides. So that's how we can simplify a computation of the volume if we have a Gram-Schmidt orthogonalization at our disposal. So let's now do the same with the determinant of the matrix, with columns being these given m vectors, or rather, m vectors which are of dimension whatever. So for the determinant to make sense, we have to assume that they are also m vectors. That is the sort of special catch here, but it's not much of a special thing. We can always, if they are linearly dependent, we can always think that they are bases in some m-dimensional vector space. So for that sake, that is not much of a stretch, but we will have to now assume that these vectors are sort of coordinate vectors of length m, and that is a matrix of square size m, and we can talk about its determinant. We can also follow this process of Gram-Schmidt orthogonalizing them, and if you remember how this process works, at each step you do an elementary transformation, so you transform any vector with the help of any other vector, so it will be elementary transformations of rows of this matrix, and that will turn our original collection into its orthogonal version through the Gram-Schmidt process. So again, we're doing Gram-Schmidt process, turning one by one, starting from the second and from the first rather, and then going to the right, and not changing the determinant, because the elementary transformations of row addition type are not changing determinants. So that is what we're going to do with the determinant of this matrix. And let's look now more at this matrix. So let's, or rather its orthogonal version. Let's call this matrix with columns being these orthogonal vectors m. The trick now is to look at the product of m and its transpose. It actually works for any. We don't need to assume anything about the vectors. The statement is that the matrix is so maybe I should swap transpose and m. Let me do this for simplicity. So what happens in the transpose matrix, I have E1 as the first row, and then E2, and all the way down to EM. In the matrix, original matrix M, I have them vectors as columns. So when the product is computed, the rule of multiplication of matrices can be now phrased in terms of scalar products. The first entry of the product will be the product, scalar product of E1 with itself. Because what we do, we compute the product of pairwise products of coordinates of the first row of this matrix and the first column of this matrix and take the sum. That is nothing but the scalar product of the two vectors. Then we have the scalar product of E1 and E2 and so on through the first row of the result. In the second row of the result, we have to compute these scalar products and so on. And you could see that in the ij position, you will have ith row taken EI and jth row taken from jth column taken from here EJ, and then you will have EI times EJ in a scalar form. But because our EI vectors are orthogonal to each other, all off-diagonal entries in this product will be 0. So what we'll have is just a diagonal matrix with these scalar squares on the diagonal. And these scalar squares are nothing but squares of the norm. So let's just put it all together. If we look now at the determinant of this matrix, which by multiplicativity and by the fact that determinant of the orthogonal is just the same as the determinant of n, will be the determinant of n squared. And that is the same as the determinant of this matrix. That's what m orthogonal times m is. And determinant of diagonal is just the product of these scalar products. And they are squares of norms of these vectors. And now we have the statement that the determinant squared is the product of those, which is the same as the volume squared. Just jumping through this sequence of equations, I could say that this is the volume squared. And this is the squared determinant of the original vectors. So I'm changing to the determinant of m, but the determinants are the same. So we have the equation that the volume squared is equal to the determinant squared. We can take the square root of that equation, and volume is always non-negative. And then we have the answer for the volume in terms of the determinant, that it is the absolute value of the determinant. If it is negative, it has to change its sign to match with the volume. So that is the result of putting together several facts from orthogonal linear algebra. See you later.